Hello everyone, thanks for having me. My name is Marshal Arijona Sinaga. Today I will present my paper with the title This Square Adversial Autoencoder. This paper was authored by me and my colleague, Mr. Lim Johannes Stefanus. Both of us come from University of Indonesia. The outline of this presentation are as follows. First, I will talk about the introduction of this paper. Second, I will talk about the method that we propose on our paper. And the third part, I will talk about the result and analysis of our experiments. And finally, I will give the conclusion of our research. So let's get started. Deep learning has made a tremendous result on supervised manner, especially on image classification. However, the progress of deep learning and representation learning still needs a lot of improvements. One of the most famous deep learning networks that can solve representation learning is called as the Autoencoder. Autoencoder tries to reconstruct the data by utilizing the latent variable. The latent variable distribution tries to estimate the distribution of the real data. Unfortunately, the continuity of the latent variable distribution cannot always be assured. This condition leads to the inability of the autoencoder to generate data by transforming the latent variable. Another well-known representation learning is called as generative adversarial network, also known as GAN. GAN is the deep learning network that can generate new samples that is similar to the training set. This can be done by transform a vector noise that is sampled from the prior distribution. The prior distribution itself is assured to be a continuous distribution. GAN has so many variants, including info gain, Wasserstein gain, energy-based gain, and least square gain. This paper tries to combine the autoencoder and the generative adversarial network. We hope by combining these models, we can have an autoencoder that has a continuous latent variable distribution that is continuous. So with this condition, we hope that we can generate a new data that's similar to the training samples or the real data distribution. The problem statements of our research are as follows. First, how to combine the least square generative adversarial network and the autoencoder into least square adversarial autoencoder. Second, how to implement the least square adversarial autoencoder. Third, how is the quality of image reconstruction of least square adversarial autoencoder? And the last is, how is the quality of image generation of least square adversarial autoencoder? Okay, now I will talk about least square generative adversarial network, also known as LSGAN. Generally, generative adversarial network is a deep learning network that consists of two main networks. It is called the generator network and the discriminator network. Generator network will try to produce a data that we can call as the x-axon, that is similar to the data x, a data that came from the training set or from the real data distribution. This can be done by transform a vector noise z that is sampled from the prior distribution and pass it to the generator function, and the generator will produce the x-axis. The generated data then will be passed into the discriminator network. Discriminator network tries to distinguish whether the data came from the generated data distribution or whether it came from the training set distribution or the real data distribution. We call this network as an adversarial network because both of these network works in an opposite manner. The discriminator will use the objective function to improve its ability to distinguish the origin of the data. The generator itself will will use the objective function to weaken the ability of the discriminator. The generator will do this by try to improve its skill to generate a more similar generate data that's more similar to the real data distribution. The difference between the LS gen with the original gen is on its loss function. LS gen uses least square loss function on its discriminator and on its generator. This loss function is often used by the linear regression method. Theoretically, by using the least square loss function on GAN, we try to minimize the Pearson divergence between the real data distribution and the generated data distribution. Now I will talk about the Autoencoder. The Autoencoder is a deep learning that has two main networks, the encoder network and the decoder network. The encoder network tries to transform a data X into a latent variable Z action by using the encoder function that we call as G theta G, where theta G is the weight parameters of the encoder. The decoder network will try to transform the latent variable Z action into a new form that we call as X action by using a decoder function that we call as Q theta Q, where theta Q is the weight parameters of the decoder. So this is the theta G, the weight in the encoder layer, and Q theta Q is the weight on the decoder layer. So the encoder tried to minimize the distance between the X and the X action. So that's why the encoder tried to reconstruct the data, since we want to minimize the distance between the X and the X action. The special thing about the autoencoder is the latent variable. Autoencoder tried to find a simple representation of the real data by transform the data into a lower dimension. So we hope that we can find a simpler representation of the distribution of the data. So now let's combine the autoencoder and the LS gain. We call it as least square adversarial autoencoder, or also you can call it LSAA. So LSAA basically is an autoencoder with an additional network that we call the discriminator. The discriminator tries to distinguish the origin of the data, whether it comes from the prior distribution or whether it comes from the latent variable distribution. So LSAA works as follows. First, it will transform data X into a latent variable Z action by using G theta G, the function of the encoder. Next, we will pass the latent variable into a discriminator, and the discriminator will try to find the probability that the latent variable comes from the latent variable distribution. This network is also will try to guess the origin of the vector noise Z. It will try to find the probability that the vector noise Z came from the prior distribution. And on LSAA, the encoder also works as the generator. It means that the encoder will try to transform the data X into latent variable Z action such that it will confusing the discriminator. What I mean by confusing is the discriminator, the generator or the encoder will try to minimize the probability of the discriminator find that the latent variable come from the latent variable distribution. So the encoder will improve its ability to generate a data that's similar to the prior distribution. The latent variable Z action then will be passed again into the decoder using the function Q theta Q. So it will produce the reconstructed data that we call as X action. So basically, there are two objective functions of LSAA. The first is the reconstruction error, minimizing the distance between x and x-axis, and the second is minimizing the divergence between two distributions, the latent variable distribution and the prior distribution, specifically minimizing the percent divergence between these two distributions. So we hope that by minimizing this divergence, by minimizing this percent divergence, we can we can generate data by sampling from the prior distribution and pass it to the decoder. Now let's talk about the architecture of LSAA. So on the architecture of LSAA, we use the convolutional layer on the encoder and decoder. We use the convolution layer on this network to find a better feature extraction. So, while on the discriminator network, we don't use the convolution layer since the dimensionality of the latent variable is 20, which is small. For the prior distribution, we use the Gaussian distribution with the mean 0 and standard deviation equals to 1. Okay, now let's talk about the metric. So the aspect that we want to measure on LSAA is the reconstruction ability. We measure it by mean square error, with the ideal score is 0, which means that two data is identical. The second aspect is the generation ability. We measure this ability using threshold inception distance. Also with the ideal score is 0, which means that two distribution is basically the same or identical. So now let's jump on the experiment section. On our research, we developed a Python program to model the LSAA. For the software tools, we use PyTorch as its frameworks, and we executed the program on Jupyter Notebook. For the computing resource, we use DGX1, provided by Tokopedia IEEE Center. On our experiments, we use two dataset benchmark, MNIST and Fashion MNIST. MNIST is a grayscale dataset which consists of the image of digit numbers, and Fashion MNIST is also a grayscale dataset which consists of fashion items. Both of the data consists of 70,000 data, with 60,000 are used as a training data and 10,000 are used as the test data. So here's the reconstruction result of our models. We found that our model achieved mean square error of 0.008 on MNIST dataset and 0.000099 on Fashion MNIST dataset. We also compared that our results with the experiments conducted by the fellow and his colleague. We set our testing environment the same with theirs. So we found that our model beats the variational autoencoder on both of the datasets, and but the Wasserstein autoencoder performs slightly better on both of the dataset. So here's the example of image reconstruction performed by our model. So we can see that most of the image can be well reconstructed, but there is some exception on this image where even the model could reconstruct the data. The reconstructed data seems that it lost some details. It's because the dimensionality of our data variable that is relatively small. Okay, now let's talk about the generation results. We found that our model achieved FID 11.128 on MNIST dataset and 27.5737 on Fashion MNIST dataset. We also compare our results with experiments we conduct by Lucic and his college. Also, we set the testing environment the same with theirs. So their experiments tried to compare the FID on the generative models on the MNIST dataset and Fashion MNIST dataset. So the research found that Wasserstein GAN gives the best result, and the worst result is achieved by the variational autoencoder. So By using the scores and the comparison and the comparator, we can say that the LSAA could generate data that's similar to the real data distribution. This is the examples of our image that is generated by our models. We can see that most of the images are well generated, except for some image that seems that's so difficult to recognize as one of the fashion items. So this is the conclusion of our research. First, the contribution of this research is the investigation of least square adversarial autoencoder, an adversarial autoencoder that uses least square generative adversarial network loss function on its discriminator and generator. Second, in this research, a Python program was made to model the least square adversarial autoencoder. The program was implemented using Python's framework. The program was executed using Jupyter Notebook. The program utilized DGX1 computing research provided by Tokopedia UI AI Center. The mean square error results show that the least square adversarial autoencoder has good reconstruction capability. Fraction inception distance results show that the least square adversarial autoencoder is also able to generate images similar to the training samples. So this is the end of my presentation. Thank you.